Let me make a comment, if I might, on the previous presentation. I feel very much sorrow for the suffering Tricia has gone through. I've never been associated with causality, et cetera, associated, but I have been part of the production at Hanford as a part of my career. In fact, for the first 10 years of my career at Hanford, I came here in 1979, that dates me. I was at the N reactor, and I was the engineering manager for the reactor, and eventually was the plant manager at the reactor when we shut it down in 1988, 1989. But then, and this presentation is actually my personal story, because then I made the transition at the same time that the Hanford site did, and made the transition from production to cleanup. And so while I spent 10 years of my career on production, I have spent 35 years in environmental cleanup. And if you ask me what my job is, it is an environmental cleanup manager specializing in nuclear radiation cleanup projects. So with that, I'm going to kick off environmental cleanup strategies and the progress at Hanford. And I'm not going to spend a lot of time showing you the state of Washington and where Hanford is. This is a nice picture. This is the Hanford vitrification plant. I'm going to be talking about that some more in a little bit. I'm currently on contract with the Department of Energy. They have restarted the design of the high-level waste vitrification facility. And for the Department of Energy, I help with overview of that redesign. This is the plutonium finishing plant. Just to point this is the Purex plant, where the vast majority of plutonium separations occurred nationally for the United States, but specifically here at the Hanford site. And I'm going to talk a little bit about it, but the famous Purex tunnels, you can't really see them, but they're right in this space here. I'm going to also be talking about the Hanford tank farms. And this is a sea farm. The Purex plant was actually called the A plant, but we all know it better as Purex. And so its waste from the plutonium separations was originally sent to the A tank farm. Well, it's the Cold War and you still want to make more plutonium, so you fill up the A farm with radioactive waste, and then you build AX farm. And you fill that one up, and you build AY farm, and you fill that up, and you make AZ farm. And now you've run out of the alphabet, and so you go back and you build AW farm and AP farm. And all of those are in this space here. And from about 1993 to about 2005, I was the chief engineer for the Hanford tank farms. So just to give you a little bit of background where I come from as we go forward here. This is the history is one of the Manhattan Project sites during World War II, of course. And it was really the goal and the purpose was production of plutonium for atomic weapons. Roughly 67% of all the plutonium produced in the United States were produced here at Hanford. It is also the largest nuclear cleanup project in the country. By any reasonable measure, it is one of the largest in the world as well. So let's talk about production. Hazardous and solid liquid wastes were produced as part of the process. I often give tours out at the B reactor. We just had the last tour today. And I like to point out that the fuel that went into the very first large power production reactor in the world, the very first plutonium production reactor, Each fuel slug weighed 9 pounds. And each of those fuel slugs, when chemically separated, would result in 1 gram of plutonium. So it was not a very efficient process for the plutonium. And of course, that was the goal. Well, what did you do with the rest of the 9 pounds of that original fuel? Well, that, plus the chemicals necessary to separate it, were all sent into these tanks. And these are pictures during construction of the single shell tanks. The original tanks were carbon steel because during World War II, stainless steel was very expensive and very difficult to come by. And so the decision was to use carbon steel as the basis for the tanks. What's the big deal with that? Well, the chemical separations process started with dissolution in acid, and it was an acid side chemical process. And you can't put acid into a carbon steel tank, and therefore you had to neutralize it. And so, again, significant chemicals were added in that process. So that's give you a little bit of the history of the tanks. This is an interesting one, which is cleanup. So once you've run the process to separate the plutonium out, you've actually made a liquid, plutonium nitrate. And that was what was originally sent to Los Alamos. If you've ever seen the Oppenheimer movie, that's what they would receive. And then they had to then refine it down into plutonium metal. In 1949, a facility was built at the Hanford site to perform that function. This is the plutonium finishing plant, which actually the vast majority of plutonium from liquid into metallic plutonium, that was actually done in that facility. Some years ago, about 10 years ago, I actually retired from Hanford. And then one day I get a phone call that says, well, we're tearing down, and it's about at this stage, by the way, that this picture is taken. We're tearing down the plutonium finishing plant, the most contaminated facility in the United States, and they've had a contamination spread. Would I please come out of retirement and be the engineering manager for the final cleanup of the plutonium finishing plant? And so, yes, that was something worthy of me coming out of retirement to go do. And you can see it was an open air demolition process that was used. And you can see what you did is you tried to keep the contamination levels down by using basically a water spray process to keep track of that, and with a very large exclusion zone around the facility. So that's just one example of cleanup. Now I'm going to ask my good friend, I got some gifts for those who came here today, and the plutonium finishing plant is actually on this little postcard we've put together, so you can see what it looked like before, and if you tilt it just a little bit, you can see what it looked like afterwards. And so I have gifts for those who bothered to come here today and listen to me drone on about my favorite topic, which is Hanford cleanup. So thank you. 1989, I went from production. I was the plant manager for the end reactor. And I was asked to come to tank farms and help them with an interesting problem they had. I told you that these were carbon steel tanks. Well, unfortunately, the welds to put together the tanks were cracking because of a phenomena that was not known in the 1940s, wasn't actually known until the 1960s, called nitrite-induced stress corrosion cracking. So the separation process used nitric acid to dissolve the fuel from the reactors, first step in the separation process for plutonium. I'm sorry, I'm an engineer. You're going to learn a little bit of engineering here. And as a result, there's a large nitrite chemical constituent in these tanks. Unfortunately, the welds had not been annealed originally, and not until we started building tanks in the 1960s did we correct for that problem. So the 144 single-shell tanks, I told you, you want to keep making plutonium, so you keep taking the waste from that separations process, and you fill up a tank farm. Showed you a picture of a tank farm. You know, each tank is about 1 million gallons. And eventually you end up with cracks in those welds. And single wall means there's only one wall. This room would really nicely fit in one of those tanks, by the way. So it just to get a feel for them. And then they're typically 60 feet tall or so, depending on the waste volume in the tanks. So in 1989, I went from producing plutonium to trying to figure out how to clean it up. And you can't understand cleanup at Hanford if you don't understand the legal framework under which it is done. And so in 1989, I, as a contractor, was asked to be the lead negotiator in the tri-party agreement. Now, the tri-party agreement is the cleanup agreement for Hanford. In 1989, the Department of Energy chose to make a dramatic change in how they manage their radioactive and other wastes at the site. They chose to comply with the environmental regulations of the United States. Prior to 1989, they were not required to comply. The process under which the Department of Energy set up the cleanup standards, the milestones, and requirements is now called the Tri-Party Agreement. Why is it tri-party? There was a decision that the cleanup decisions would not just be a federal Environmental Protection Agency decision process, that it would also include the Washington State Department of Ecology. So the three parties in the agreement are the U.S. Department of Energy, who is responsible for the actions, and the Environmental Protection Agency, and the Washington State Department of Ecology. Now, there's two major regulations under which this is done, RCRA and CERCLA. I'm not going to get into the details of that in this presentation, but there's two major environmental regulations, laws in the state, in the United States that apply to environmental cleanups. And so the formal agreement was put together. It's a legally enforceable agreement associated with governing the Hanford cleanup. It establishes roles, responsibilities, authorities for the three agencies. For example, the tank farms and its associated cleanup is primarily under the aegis of the Washington State Department of Ecology. And it developed an action plan for implementing cleanup actions and enforcing milestones. And it has frequently gone to federal courts for enforcement of various activities associated with the cleanup. There's also a community relations plan. I'm not going to get into that because other speakers in this series will spend more time going into that. So I'm not going to talk too much about that in this particular talk. But I'll say this was the right thing to do. It was a decision Mike Lawrence and others in the Department of Energy put through, but they didn't have to. They could have done an exclusion, which was also in the law, and they chose not to use an exclusion that's in the Atomic Energy Act. Instead, they chose to comply and have regulatory oversight. Before 1989, if I wanted to bury something new out into the desert, We went to the Department of Energy, said this is the best way to do it, and they would sign off on it. Today, if I want to dispose of something, we either have to go to the EPA and say, this is what we want to dispose and how we want to dispose of it, and they review our designs, or in the case of the tank farms and everything associated with that, including the vitrification process, the Washington State Department of Ecology. And they actually issue a permit that allows us to go do it and allows the public involvement in that decision-making process. And so that's a radical change in how cleanup was managed. I can't tell you how different it was and how essential it was in this whole process. So I'm going to do a little bit of Hanford cleanup overview. And if I throw some science and engineering in here, well, I'm sorry, I'm an engineer, and so you're just going to have to understand. They ask an engineer to give you a talk, so there it is. Solid waste can be everything from reactor equipment, contaminated clothing, workers wore during the production activities. That's really common. Solid waste buried in the ground in pits or trenches. That's been a major portion, and it doesn't look sexy. I mean, let me just tell you, it was underground, so we took a picture before, and all you see is a bunch of, we killed all the tumbleweeds, et cetera, et cetera. It just looked like, desert. And then we dig it all up. We find stuff in boxes, cardboard boxes, wooden boxes, falling apart, 55-gallon drums quite frequently. Most of the time they're in good shape because the soil is pretty dry around here, but quite frankly, sometimes they're not in such good shape and you have to repackage all that. And then what do we do with it? Well, we have a facility on site that is permitted by under CERCLA for disposal of radioactive solid waste, Environmental Restoration Disposal Facility, ERDF, we will call it all the time. And so it all gets repackaged in accordance with requirements in our permit, and now we can bury it again. So it just, it doesn't show really good in pictures, right? But it is really, by volume, the biggest part of cleanup of Hanford is the solid wastes and the burial grounds associated with that. Now, the biggest dollar value, so I just told you it's the biggest by volume and by mass is the solid waste. But I'll tell you the biggest by cost is, without a doubt, the liquid waste. Now, in the tanks, we say it's liquid waste, but that's not quite right because there were solids that precipitate out of the waste. Then we categorize that in the liquid waste categories for the purposes of this. And one of my early jobs was to figure out how, we've made an agreement. We're going to get the waste out of those single shell tanks. They're non-compliant. If you wanted to build a new radioactive waste storage tank, you cannot build single shell tanks. In fact, if you're going to put in a new gas station, you can put a tank in there for the gas, but it has to be in a vault that can also handle the leaks from such a tank, right? Well, that's the requirement. It's been a requirement in the United States for decades. Well, the single shell tanks built from the 1940s through the 1960s are non-compliant. And just to make you feel better about it, the design life was 40 years. Now let me think about that. First one was built in 1944. It first received waste in 1945 mostly. 40-year design life. You get the idea. Regulatorily, we got to get the waste out of those tanks, okay? And so one of my first jobs, when coming from the reactors, was how are you going to get the waste out of the tanks? And it's not like you're pumping petroleum out of a petroleum tank, which is a non-trivial thing. But this case, you're dealing with exceedingly high radiation levels associated with these tanks. I see somebody drinking from a water bottle over here. That's always very good. You know, if that was one of the wastes from one of my tanks, first you wouldn't drink it because it would taste really bad. If you were to pour it on your hand, it's so caustic it would eat right through your hand. You would have received a lethal dose in a matter of a few minutes. There you go. I think you appreciate that. And so it's a non-trivial business because everything is done remotely. And so one of the first things I did was to build a mock-up facility. And so you can actually go out and see a Hanford single-shell tank. I built one just so that we could test various technologies. And we're still doing that, still trying to find better ways to get safely the waste out of those tanks. We're going to talk a little bit more about progress on liquid waste. But as we said, it's mostly in underground storage tanks. They will be eventually transferred into glass-like material. And so my very kind friend will pass around. You can't keep this one. You could keep the postcards, but you can't keep this. This is the ultimate goal for the tank waste, and it's called borosilicate glass. And the idea, and this is where they hear vitrification, that's the technical term for making glass, is to make vitrified. And what you're passing around is actual. This was one of my projects some time ago while I was still out there. We put together the chemicals correct from the tanks, but non-radioactive, and then we started making glass out of it to see if the chemicals would, first off, at glass temperatures, much of it just disintegrates as a chemical, and it just ends up as elementals, and it goes into solution. Glass is a very interesting material. It's called an amorphous solid, which simply means it actually can move. Now, like water, well, yes, over millions of years time frame, glass is amorphous, but when you take the material, it actually dissolves in the glass matrix, and it releases the hazardous material, and radioactive material would be in there, at the rate that glass corrodes. Okay? And we have examples of Roman glass, and we can figure out how much glass from thousands of years ago has corroded. And the answer is it's a fraction on the order of 1/1,000,000th of an inch has actually dissolved or released. You could take that and put it in the bottom of the Columbia River, and it would not be measurable downstream. Not that I'm proposing that that's the disposal mechanism, but you get a feeling for it. It's a spectacularly good disposal medium for these kind of wastes. It's not cheap. Let me repeat that. This process is not cheap. The current budget at Hanford is about $3 billion per year, and a good fraction of that goes into the waste vitrification plant. Good news on waste vitrification is there's two levels of waste. There's called low level waste and high level waste. And the low level waste vitrification facility is making glass, non-radioactive glass. We're hoping sometime in early next calendar year, they'll actually start putting radioactive materials into glass for disposal. So now, the last one. This is that picture I showed you of the plutonium finishing plant. That's a facility. And so we have a lot of facilities. The reactors the plutonium finishing plant, lots of buildings. Now that's really sexy. That's why I can show you these postcards I handed out, right? If you tilt it just right for the PFP, you can see where the building was there, and then you can see the engineered design. It's the regulatory agreement is we'll take these buildings down to slab on grade. That means a concrete slab at grade is the current step. Now, that's not going to be the final one, but part of the negotiation process is to make sure that we are doing things, that we're spending our money where we get the most risk reduction. And that's a significant factor in the decision-making process. Now, most of these radioactive facilities have some level of contamination in the soil around them. And so eventually the agreement is we're taking down the building because that's the most significant hazard now. And then when we've got enough other work done, the money will go into actually digging up the contamination in the soil as well and packaging that up and disposing of that as well. We do a lot of that as it is right now. Well, there is a lot more to be done in the future. So that's the facilities aspect. Okay. So, Hanford cleanup by the numbers. We keep track of our metrics. We're project managers, almost all of us. And so, what is our progress? So, I'm going to talk about each one of these as we go, but you get a feel for it. April 15th, 2024, we've got an update that we did as of October, actually, for this as well. But you get a feeling for underground waste storage tanks, and I'm going to give you some updates as we go along so you can see that we've made progress even since last April. Reactors in upper left, tons of contamination removed from the groundwater. We're going to spend some time talking about, well, if you contaminated the soil, did you contaminate the groundwater? And the answer is yes. Not proud of that, but that is the fact. What I am proud of is the billions of gallons that we've pumped out and cleaned up over the years. The solid waste, and this is the, is that a really fun picture? That's the disposal at ERT of solid waste. The underground storage tanks, facilities demolished. We're going to talk about PFP, the waste sites remediated, and finally the waste treated associated with the process of vitrification. So that's just kind of my overview. So in the next half hour, we're going to take you through all of this. And this is what I'm talking about is about a $3 billion a year cleanup effort. This is a non-trivial effort, right? Involved in tens of thousands of people working at the Hanford site. So the reactor decommissioning at Hanford. This is where I talked about 971. So there were 9 production reactors built at the Hanford site, 8 of which really are kind of copies of the original B reactor, and they were called single pass reactors. Well, that's a single pass reactor. I was originally hired by the Atomic Energy Commission, that will date me something seriously, to work on the personal staff of the Division of Naval Reactors. And as an engineer, they hired me as an engineer. That was really wonderful. And then they said, we like you so much, we're going to send you to graduate school. We're going to pay you as an engineer to go to school, and we'll pay for school. What a deal. I'm sorry, students, I came out of that with no student debt. But they got to pick, however, what I studied. You get to pick what you study. I am your personal nuclear engineer. Thank you, Admiral H.G. Rickover in the Division of Naval Reactors. Okay, so I told you, single pass. So I had my first child back in Washington, D.C. while I was working there and decided I didn't want to raise my child there. I wanted to come to this beautiful area out here at Hanford, Richland, Pasco, Kennewick area. And so I hired in 1979 at the end reactor. And I looked along the Columbia River and I says, oh, you got some other reactors out here. They said, yeah, they've all been shut down. We shut down the last one of them in 1971, 8 years ago. And I says, well, that's great. Why'd you shut them down? He says, well, they were polluting the Columbia River, amongst other things. Really? How did they do that? Well, we would pump it out of the river, filter it, add some chemicals, not good chemicals in many cases, okay, run it through the reactor to cool because the heat was a waste. They didn't make electricity out of it. They just wanted to make plutonium, right? And so they took the river water, ran it through the reactor, came in at around 60 degrees, Columbia River temperature. 1 second later, it was 190 degrees Fahrenheit at 250 megawatts at good old B reactor, and 4,000 megawatts at the K East and K West reactors. And what would they do with the water when it had been gone through and gotten heated up? Send it back to the river. And I says, you can't be kidding. That's not the way I went to nuclear engineering school. That's not the way you run a reactor. That's what's called a single pass reactor. 8 of them were single pass reactors. Fortunately, I got to work and be the plant manager. I'm very proud of this. At the N reactor, the 9th of them, and it was called the N reactor because it was the newest one. Okay, and so we took our primary coolant and ran it in circles at 2,000 psi, and then generated electricity out of that heat. So we made plutonium, but we also made electricity, but we did not pollute the Columbia River like the other 8 had been through that process. So the 9 production facilities, there's 9 reactors, 7 have been cocooned. And so one of your postcards I handed out to you is the most recent cocooning we actually did. That's the K East reactor. So all the ancillary facilities, the pump house, the filters, the chemical addition facility, we tore all that stuff down. It's mostly clean tear downs. But the reactor itself is still highly contaminated in the core of the reactor. And so the environmental agreement was we're not going to disassemble that now. We're going to protect it, isolate it from the environment as best we can. And this is that picture, that postcard you got. This is the K East reactor before, and then we built a building. That's not something fake. That's very real. So we built a building around the building to keep it weather protected and to keep it isolated from the environment for 75 years. So the decision that was made in conjunction with the Environmental Protection Agency, subject to public comment and release, was let's not endanger the workers to tear apart those reactors now. We'll wait 75 years. The bad thing about radiation is unless you got a detector, you can't even tell it's going on, right? But the good news about it is it goes away. I always like to point out the difference between Botox, which is a very, very serious chemical hazard. And once you've made some Botox, it's going to be around forever, unless you do something to try and destroy that chemical. But the radiation will destroy itself with a half-life. And in this case, cobalt-60 is the primary contaminant of concern inside the reactors. And if you wait 75 years, you've gone through, so 75 divided by 5, you get the idea of the number of half-lives. There's kind of a nuclear engineering rule of thumb. 10 half-lives is 2 to the 10th. It's a big number. You're dividing by that number, and you're pretty close to 0 by that time. In this case, we're going to go to about 15 half-lives. And so the cobalt-60 will have destroyed itself. It will no longer be radioactive. And so the decision is isolate it, wait. And that's a good decision, but it was a decision not made by the Department of Energy. That was a decision made in conjunction with the Environmental Protection Agency, the Washington State Department of Ecology, and subject to comment from the public associated with it. I happen to be an advocate for that originally, so obviously I think it's a good decision, but you get the idea. Well, hold it. We said there were 9, 7 are cocooned, including my N reactor. So what's going on? Well, it turns out there was a fuel storage basin next to the K West reactor that had been storing spent fuel from the N reactor and other reactors. And the last project that I was on, that I had before I retired, was the process of getting the sludges and the particles out and getting the fuel out of that last fuel storage basin. And so quite proud of that. We've now emptied that fuel storage basin of liquid of the radioactive material, disposed of it appropriately in accordance with our environmental control agreements on site. And they are now, we have dewatered that fuel storage basin. Fuel storage basins everywhere in the world is fuel stored in a liquid medium because it's both a shield and it takes out the heat. And back at Fukushima, that's one of the big problems that they have to deal with is the fuel storage basins at the Fukushima reactors. So we've now done that, and we are grouting, filling that fuel storage basin with grout, and eventually we will cut up the grout into chunks that can go on the back of a truck, and we'll take it up to the environmental restoration, ERDF, the land disposal facility for solid waste here at Hanford. That process has been used at the other storage basins, so we're close to actually taking out and cocooning the 8th of the 9. Well, hold it. What about the 9th one? That's the B reactor. The National Historic Monument and part of the U.S. National Park Service. It's owned by the Department of Energy, but it is the very first power reactor in the world, amazingly built during World War II in less than a year for plutonium production, and that will be preserved. It will not be torn down. It will not. We're not going to build a big building around the top of it to isolate it from everybody else. Instead, the government has decided to put the money into maintaining it as a national monument, as a place. Megan and I actually do tours out there from time to time. So thank you. So 7 in ISS, one of them currently undergoing decommissioning, and the 105B reactor, first full-scale nuclear reactor, is to be preserved as part of our history. It is, in my opinion, the dividing point between the atomic age and before is actually the startup of the B reactor. Interim safe storage, I've talked about that, 75 years, cobalt-60, priority placed on remediating nearby waste sites. Every one of the reactors had its own waste site associated with it. Personal story, it's a good one. One of the liquid waste sites for the N reactor, my reactor, when I was the first engineering manager, we came out there and they said, well, we take our radioactive waste and we send it out to a crib. What's a crib? It's just basically a trench in the ground, okay? And we said, oh, well, that's interesting. Well, the soil is getting full, and we would like to not keep filling up the soil because maybe it'll bust through and head to the Columbia River, like 50 feet away from the crib. So I built a new crib. And so we built this nice crib. And I says, well, we're going to put a cover on my crib. We're not just going to pump liquid out there and have it head out. So that was really cool. And so I thought I was really proud of that. That was one of my projects. And then one day, an airplane lined up to land on my crib. And we said, oh, we didn't design it for airplanes to land on the crib. So we went out and put up signs and all that and said, that's a bad idea. So we built a new crib with zigzags in it so that it didn't look like that's just one of my personal stories. Okay. I thought you might appreciate that. By the way, those cribs have all been dug up. All the contamination in the soil around those cribs has been packaged, and we took it up and disposed it at the EPA regulated ERDF disposal facility. Nuclear facility D&D options, okay? So we're going to talk a little bit more about that. The EIS for large surplus production reactors, they were graphite moderated, interim safe storage, 75 years, reduce the footprint. So why is this? Take a look at all these ancillary buildings and things around it, and it's actually even more than that. And we take everything out except the core region of the reactor. So get a feel for what, and that's a non-trivial effort. Several hundred people working for a couple of years to go from there to there. But it makes really good pictures. And we can make postcards showing you how, you get the idea. Very proud of that, okay. Groundwater contamination, okay. So when I first got into tank farms, I asked the question, well, where do the Hanford tank leaks go? And somehow I got to be, for about 10 years, I got 15 minutes. Come on, Mark, I see you looking at it. I came from the reactor over to tank farms. And they said, and they drugged me over there. They really said, you know, the reactor's done. You know, we're going to tear it apart and everything. But what we need you to do is work on those leaking single shell tanks. And I says, well, you can't stop the leaks very easily. You just got to get the stuff out of them. I says, we got no place to put it. Well, really? No, we got, there's 177 tanks, 144 of them are single shell tanks. Let me think about that. They're all about 1 million gallons. I'll just make the numbers a little easy to see. There's no room in the double shell tanks. They're all full too. So there's no place to put them. Really, there's not much space left. I said, well, we can build new double shell tanks. I sat down and during the negotiations, I calculated that. How much does it cost to build a new double wall, stainless steel, maybe even carbon steel to keep it cheaper? About $100 million a copy. Now let's think about that. So we're going to move the waste out of the single shell tanks into new double shell tanks at a cost of about $144 million just to build the tanks. That didn't get rid of the waste, it just got them out of one place and stuck it in another. You get the idea. And so, number one. Number two, how many have leaked so far? Ah, yes, Rick, you're in charge of figuring out how many have leaked already and how many are leaking now. And so I got the fun job for about 8 years. Every 3 to 6 months, they would drag me in front of KNDU cameras and I'd say, yeah, we got another leaking tank. And everybody says, that's terrible. Why are you letting them leak? No. I says, come on. Nitrate, nitrite, stress corrosion cracking, they all probably, and they says, well, how many of them are going to leak? And I says, they've all probably leaked some amount. We just haven't been able to measure the amount that they have leaked yet. Oh, okay. And then here was the next part. I asked the soil geologist people, I says, well, where's the leaks going? Is it going into the groundwater? Now, I think of the map of the Hanford site that I showed you. And of course, there's the beautiful, clean Columbia River. And we all, don't touch that river. That's our legacy. That's our beauty out here, right? The groundwater is eventually heading towards the Columbia River. That's the bad news. The good news is, how much does it rain around here every year? 6 to 8 inches. How long does it take to get from Rattlesnake Mountain to the Columbia River? About 300 to 400 years. So those leaks are on the Hanford site. And they have made it, in many cases, to the groundwater, and they're continuing to get there. So what you can't stop the leaks, you can't stop it from getting to the groundwater. What you can do is stop it from getting to the Columbia River. And so this is the Hanford groundwater contamination and treatment strategies. 680 tons of contaminant has been removed from the groundwater. As of last April, the updated to October is 688. The 33.7 billion gallons of water, and I give tours out on the Hanford site, and we pump it out, treat it, take out the contaminants, and then what do? It all meets drinking water standards. And so whenever I go on the tours, I say, well, this is government water. The government paid for it. And we treat it to drinking water standards, right? Don't worry about it. This didn't come from the Hanford. We pump it right back into the ground. Why do we pump it right back into the ground? The answer is you can use the clean water to push the dirty water towards the extraction wells. And so you surround the plume of contaminants with wells that inject clean water, and they push the water to the wells that are in the middle of the plume associated. So the priority is the river corridor, and so we have several of these treatment facilities along the river. And here's if you want to know more about this, we got an annual report that goes out. And now, as of October, we're at about 35 billion, another 2 billion gallons this year has been pumped out of the ground. Billion is a big number. And so this is where we get to say, yes, cleanup includes billions and billions. They average about 2 to 3 billion gallons a year out of this system. So where is it? Single shell tank leaks. I told you I was in charge of single shell tank leaks. So another personal story. So they wanted to have a program, and they were going to put me in charge of this program. And of course, it's Hanford, so you get an acronym for every new program you come up with, right? And so they asked me to be in charge of the leaky underground storage tank. And I says, I refuse to be the lust manager for Hanford. So leaky underground storage tanks, and we don't call it that, but it is the single shell and double shell. Double shell tanks haven't leaked to the environment, but the single shell tanks obviously have. The production reactors, and that was part of me. We added liquids to the ground in cribs and trenches associated with that. Carbon tetrachloride, technetium, cobalt, chromium, and they like to just say chromium. It is, if you kind of dated now, maybe you're all too young, the Aaron Brockovich movie, yeah, that was hexavalent chromium. It's a carcinogen, didn't know that at the time, but it was used in the single pass reactors because, and same reason that for the people Aaron Brockovich brought a lawsuit against, because it's a corrosion inhibitor. And it was used to inhibit corrosion at the reactors historically. So that's a significant contaminant, what we call a contaminant of concern. We're very concerned about the contaminants. What you won't see, you'll see here, this includes the iodine that was the previous discussion. So it is in the groundwater as well. The treatment process takes the iodine out, and we treat that separately as radioactive material, and it is packaged and disposed of appropriately at the ERDA facility. And buried solids and waste, pits, burials, and I told you that's it. They kind of say 55-gallon drums, but it was really a little bit of everything. And you get tritium, technetium, cesium, strontium. You get all these good guys, right? Transuranics. That's an interesting little twist. They got me 5 minutes more, so I won't tell you the personal story. Okay. Groundwater plumes, to get a feel for, there are plumes. They're on the Hanford site, and of concern particularly are the ones that are close to the Columbia River, but you get the idea. These plumes eventually will go there, and so we're attacking those plumes as well. And I'm just going to show you some of the. So overview: 170 square kilometers of groundwater. Largest plumes are tritium, iodine, 129. 131 has a fairly short half-life, so it's not really much of an issue anymore at Hanford, to be honest with you. Smaller plumes are present containing technetium, which is a bone seeker. That's the number one we concern about for long-term. Plumes that reach the Columbia River are from hexavalent chromium. I told you about that. Hanford groundwater is not expected to become a source of drinking water in the future. One of the decisions to be made is, what are you going to do with this land? And the answer is, you don't want farmers to put their farms out here and put wells down 200, 300 feet and pump it up. And so long-term maintenance will have to be done here at the Hanford site. There's a process for doing that. So sequestration is also a possibility. We've tried that system in the 300 area. There's a pump and treat in 100H, 100D, 100N, which was mostly strontium, and 100K, which is mostly chromium. The plumes at 100N, 100D are almost gone. We may actually be shutting down those pump and treat facilities in the next few years. It treats the large carbon tet plume, targets smaller tank origin plumes of Tech 99, et cetera, et cetera. A significant amount of effort. We put in somewhere around 50 to 100 new wells every year to check where the groundwater is, where it's going, et cetera. This is the pump and treat facility, and we're very, very proud of that. It was built with AARA money. You remember that there was kind of a depression in the country after the failure of the mortgage system. So they put some money out. This was all designed, but was just simply waiting for the money, and so we could build that very quickly. We're very proud of it. Solid waste, 189 million tons of solid waste, 953 facilities. That's where we can take pictures and show you that we're cleaning it up, because there used to be a lot of stuff there. Now the building's gone. So we're very proud of that. Disposal enables Hanford cleanup. Visible progress. This is that environmental restoration disposal facility. It has a permit from the Environmental Protection Agency, and this is where Hanford's going. Almost all of Hanford will be buried at this facility. And when I give the tours, I go out there and say, you know how much it costs to dispose of a cubic foot of radioactive waste at Hanford? About half as much as it takes to get rid of household waste at the Richland garbage dump. So we're not always terribly inefficient. Sometimes we can do things just right. This is what it looks like, ERDF operations. Tank waste remediation, I'm going to talk about that. I was in charge of that for a while. This is one of those single shell tanks. And I know it's kind of hard to see it, but that's actually the steel floor. Those are welds from the original steel floor in those tanks. This is AX101. This is the before, lots of sludge. One of my projects is to try and prevent the leaks is, well, let's at least get the liquid out of them. And so I was in charge of that for several years, came up with a program called interim stabilization. And we pumped the liquids out. And so the tanks look like that with solids. And it kind of just looks like, mud. And here's the after. And there's a couple of little water puddles there, but you get the idea. June 2024, removed about 346,000 gallons of radiological chemical waste from AX101. And since we have college students associated with this, every year we have students out on the site. And this year, they came up with a new tool at Hanford that used a radar to measure the depth of the waste in the underground storage tanks. And it's kind of a tricky thing. How much are you getting out? How much you're going to need to get out? How much did you leave behind? They helped us develop a tool for doing that. And so we take a picture of them saying, thank you very much for your summers of work. Future plans, waste immobilization treatment plant. I passed around the piece of glass. They're actually making non-radioactive glass today. They're at temperature. They got 2 melters up to temperature, and they have poured non-radioactive glass. They're doing startup associated with that. They intend to go radioactive. You do this in steps. You don't just jump right into it. And so for the low activity waste glass, that would be doing radioactive, and that we're actually getting waste out of the tanks and turning it into glass. The high level waste will take some more time. Design is probably over the next 5 to 7 years, and then finished construction 2035, 2037 in that time frame. So that's the direct feed low activity waste progress. That's real progress. This, believe it or not, is a worker adding glass frit, or they switched to frit from glass formers into the melter. And he's actually standing on top of the melter, adding down the chute. Glass frit goes into the feed tanks that then feeds the melter. So we got pictures of that. Waste sites remediated, over 1,000 waste sites remediated, and part of the natural environment. So you can get involved. I've got some, I'm going to leave this up here as our parting shot, but I promised there would be 10 minutes available for questions and answer, Mark. And so I'm pretty close to on schedule for that. And so I'm going to turn it open for questions now. And I already gave you a gift, so now you owe me some questions. Yes, good. You have to shout, I'm an old guy with bad hearing.
Do you think it'll ever all be cleaned up?
Well, all cleaned up is a relative term.
Okay.
When I give tours, I'm frequently asked, when are we going to be done with the cleanup? When does the government have to, to stop spending $3 billion or however much a year? And the answer is, my grandchildren's grandchildren will still have a job out at Hanford. So the answer is it will be done. The country has made a commitment to this as part of the environmental cleanup from the production of plutonium over the years. So, but most of these have design lives of 40 years or so, but it's going to go longer than that. Yeah, great question. Thank you. I'm sorry. Yeah. Yeah, who else has got this problem? Okay, yeah, some years ago I toured the plant manager for Mayak in Russia. Mayak is the Hanford for Russia, okay? And believe it or not, they even have a bigger environmental cleanup at the equivalent of Hanford in Russia. And so that's number. In the United States, the next biggest one is the Savannah River plant in South Carolina, which has a significant cleanup. And they also have single shell tanks that they're emptying out. The difference is their vitrification facility has been operating for almost 10 years now. And so they've been making waste into glass quite a while. So, in the state of Washington?
We have 2 entities that are also working with you.
Yes. Yeah, interesting. Oregon, for some reason, decided to call their environmental monitoring agents the Department of Energy. And so it generates a lot of confusion around here because we'll have, and they are part of the process. They do sign off on some things, but most things they don't sign off on, but they provide input to our regulators every time. I get to talk with them quite frequently. But it's always interesting, he says, because here's our representative from the Oregon Department of Energy, and here's our representative from the US Department of Energy. You get the idea. So it causes some confusion. But Oregon is definitely involved. The Native American tribes are definitely involved. If you want to get involved, the Hanford Advisory Board is always looking for citizen involvement in it as well. And again, there's an interesting one. Last week, one of the reactor vessels, there's now 144 nuclear submarine reactor compartments that have been buried. They're in the trench. We haven't put the dirt over the top, so they're not really buried. But here at the Hanford site, and they come all the way from Bremerton, all the way around up the Columbia River. And the state of Oregon, because our dividing line is right there, they have to sign off on every one of those shipments as it comes up the Columbia River. It's really fascinating to see them come up and then put on this crawler. And it's really exciting to see it crawl at 1 mile per hour out to the Hanford site. Yes, Megan?
Some questions about the pump and treat process.
Yes.
Of course, we're basically trying to seek out the compounds that we don't want in the water.
Right.
How do we go about doing that?
How do we go about doing that? Yeah. Do you have a water softener at home?
Yes, I do.
Okay. Guess what? It's taking contaminants out of the water for you, right? Well, we have, they're not water softeners, but they're different materials, rheolite, et cetera, that we pump the water through, and it gets in. Really cool one, since I've got a couple of minutes. One of them was the nitrates of nitrite I told you that was in the groundwater. And so some really clever people from Battelle took the water samples up from the groundwater and looked at it and says, you know, there's bacteria down here living on that nitrates. Ooh, cool. What if we grew those bacteria and ran the water through them? And so the bacteria then takes all the nitrates and nitrites out for us. And and so to say thank you to that bacteria, we kill it. And then put it in a box and take it over to Erdf and bury it. But they take the nitrates and nitrates, very efficient. And so that was really cool. In fact, that's been so effective that last year we shut down the process. We don't have any bacteria taking the nitrates out of the water because we got it all out of the water. It's really so effective. That's a great question. No, again. Oh, yeah, good. Yeah.
It takes a lot of heat.
Yeah. Where do we get that heat? Yeah, so I got an award for that project. You got to provide, it's electric. You put basically carbon into the melt, and you run electricity through that, and you're constantly heating the glass using that. And you got to have refractory all around the outside of it. So where do we get it from? We get it from the EPA. we get it from Energy Northwest and hook into the total grid here out at Hanford. So one of my projects was to provide electricity so that system could run. So yeah. I got an award for that. You get the idea. I've been out here a long time. Yeah, another question. Good. It would have gone into the Columbia River if we didn't put pumps in there and pumped it out. But there is no doubt that there's some years ago, there was Outside Magazine wanted to take a look at the Columbia River. So I and a few of us got in our rafts and got an editor from Outside Magazine. And you can look up the article, I'm in it, and it says, Lethal Dose of Salvation is the title of it. And as we floated along, right next to my beautiful end reactor, those cribs I told you about, we actually had to put radiation signs on the Columbia River to tell people don't land here. We've since taken those down, but at the time that was kind of embarrassing. So yeah, but with the pump and treat, we pump it out now, and so yes, But there is no doubt that Hanford has contaminated historically the Columbia River. There's just, I mean, that's incontrovertible. That's just a fact. It's a big, clean river. It tends to clean itself up. When I get asked that question when I do tours, I say, you know, however, just by comparison, the dirtiest by radioactive contamination of the Columbia River ever is 1/10 of every day on the Mississippi River. And that's because farmers use phosphates. Phosphates have uranium in it. When it comes out from the farms along the Mississippi River, they pollute the Mississippi River with uranium, which is a radionuclide. So, yeah. So everything is relative. Okay, I'm not saying it's good. Okay, we should not be polluting the Columbia River, and those pump and treats are the right thing to do. We're quite proud of that. Yeah. Other questions? I think my time is up, but I want to say thank you for everybody. I really appreciate it.